Hello everyone, welcome back to the channel. Now I know by the time this video gets released, it will be an old news, but I've just received a good news that Minato Namikaze will going to have a one-shot spin-off manga. Now I am certainly excited for that, and I thought let's recreate one of his iconic jutsu in Unity. And no, it's not flying Rasengan, it's too quick. So in today's video, we will recreate the one that he originally created, the Rasengan, using the shader graph. By the end of this video, we will get something similar to this. For this, I am using Unity version 2022.2, but it will work on any Unity LTS versions. I have a project in URP, and for this, we need a post-processing volume with the modules bloom and tone mapping with the mode ACES. Okay, without further ado, let's get shading. Now looking at various references, Rasengan can be broken down in three parts: the outer edge, the core, and the swirling lines. We will start with the edge and core because they are super easy. So let's create a shader graph. Right click, create shader graph, URP lit shader graph. We will call it Rasengan shader graph. Create a material, so right click, create, and material. Let's call it Rasengan. Create a new 3D sphere in our scene. Here we go. Just reset it and assign our material to the sphere. Let's open the shader graph. Let's quickly do some setup in the graph inspector. We will just check the allow material override. It will allow us to change these settings from the inspector. Set the surface type transparent, and I don't want our mesh to receive any shadows, so let's just uncheck receive shadows. That's it for the setup. We will start with the edge, and for that let's create a Fresnel effect node. So it will give us this nice effect, and this power is similar to the power node, performs the power operation, and it will darken the value which are less than 1 as we increase the power. We want to control this power from the inspector, so let's create a float property. Call it edge power. Give a default value of something like 5. Drag it in and feed it into this power. Let's also create a color property for our edge color. Call it edge color. Set the mode HDR and give default some bluish color. Drag it in and we will multiply this with our Fresnel effect. Now for the core part, let's create another Fresnel effect node. Keep its power at 1. Now for core, we want to invert these, so we will take its output and feed it into 1- node. 1- node, as the name suggests, will subtract 1 from whatever value we feed in. For this instance, it will invert the colors. We cannot control the strength of our core using this power. We are very limited here. See? So we will create a separate power node and feed this here. Now we can control the strength using this second input. We will control this from the inspector, so let's create a float property. Call it core power. Give a default value of like 50. Drag it in and assign it. Now let's create another property, color, to control the color of our core. Let's call it core color. Set the mode HDR and give a default value. Drag it in and we will multiply it with our core. Now we have our core and our edge. Let's add this together with add node. Then we will take its output and feed it into our emission block. Let's also create another color property. Call it base color. Set the mode HDR. Give some default value. Drag it in and we will feed it into the base color block. We will also take its output and feed it into split node. And then we will take its alpha and feed it into the alpha block, so we can control the opacity as well. Save our graph and see how it looks into our scene view. Adjust our transparency a bit and yep, pretty cool. Head back into our shader graph. Let's deal with swirling lines part. For the lines, we will use the Voronoi node. So Voronoi, and we will control this cell density from the inspector. So let's create a float property. Call it cell density. Give a default value of something like 3. Drag this one in and feed it here. And just adjust the angle offset as well, so it looks kind of yep. Let's create a power node and feed our Voronoi into it. And let me just adjust this power a bit. Perfect. To make this look like swirling, we have a handy little node called twirl node. So let's create twirl node, and the strength determines how strong the twirl effect will be, and we will control this from the inspector. So let's create another float property, call it twirl strength. Give a default value of something like 5. Drag it in and assign it to the strength. Then we will take its output and feed it into Voronoi's UV. We have this effect. Now we want to rotate this. For that, let's create a rotate node. Feed its output to our twirl node's UV. Now we can rotate this by increasing this rotation value. To do that, let's create a time node. We also want to control the speed of our rotation, so let's create a float property. Call it rotation speed. Give a default value of something like 2. Drag this in and we will multiply our time value with our rotation speed, and we will take its output and feed it into this rotation. Now this swirling line represents chakra rotation. If you remember from the episode when Naruto was learning it, to master the Rasengan, user need to rotate the chakra from multiple directions. So to replicate it in our shader, let's duplicate these nodes. We'll change this Voronoi node's angle offset so it won't look identical to the one above. Then we will twirl this in the opposite direction. So let's take the twirl strength output and feed it into negate node. Negate node will multiply whatever value we pass in with -1. So in this case 5 into -1 equals -5. And take its output and feed it into this strength, and we will do the same for this feed. So let's take this multiplies output, feed it into negate, and take its output and feed it into this rotation. Let's add these two together. Now let's multiply it with our base color, then add that to our edge and core, and then finally feed it into the emission. Let's save and see how it looks into scene view, and it looks pretty weird. This is because it is trying to apply the texture based on the default UVs of our sphere. We want to apply it perpendicular from our viewport, so if I'm looking from this direction, we want to apply it perpendicular, so apply the texture from like this direction. If we are looking from this direction, apply the texture perpendicular from this plane. To do that, let's create a position node. So position node, set the space to view and normalize it. Then we want its X and Y, so we can directly feed it into tiling and offset node and feed its output to both our rotate nodes UVs, just like that. Now it is rotating from this point, so to fix that, in the tiling and offset, set the offset to 0.5. There we go. Save. Let's go into our scene view, adjust our material. Now it looks like it is exerting chakra from the core, and Rasengan is about condensing it, so we will set the speed to negative, just like that, and you can increase it a bit as well. And yep, we have our Rasengan. At least that's what I thought when I first created it, until I zoomed out. We have another issue. As soon as I move in the viewport, and it looks weird. Now I understand why it took Minato 3 years to master it. Okay, so only reason I could think of as why this is happening is that we have a sphere, and the position node provides position of each vertex of our mesh, and they are not on the same plane. They also have various depth as well. Now this is about to get serious, so buckle up. Okay, so delete these two. Now I could use a normal vector node and keep its space to view, and then feed it into our tiling and offset. It will give us each and every fragment's normal relative to the viewport. It will ignore those normals which are facing away, so basically it will try to assign the texture perpendicular to our view direction. So let's see. Let's adjust our material, and if I zoom out, yep, if I move around, yep, if I move in the viewport, yep. Now it's not very noticeable here, but as soon as we go to the perspective view and see it from the corner of our viewport, the effect becomes slightly off-centered. And the reason is similar, that it is assigning the texture perpendicular to our view direction. So it will get slightly off-centered from the corner. So to fix it, we need our texture plane z-axis to look towards the camera. So if our camera is here, then find the direction from our object to the camera, and then assign the texture perpendicular to the direction vector that we have found. We can do it in two ways. First, by script. We will find the direction vector from our object to camera, normalize it, and then rotate our sphere in a way so that the forward axis will point towards the camera, just like this. And in our shader graph, we will apply the texture relative to our object's local XY plane, so from this plane, X and Y. First, let's do just that. In shader graph, change the normal vector node space from view to object, so as we rotate the sphere, our texture will rotate relative to it. Then via script, we will rotate the sphere so that its z-axis always points towards the camera, so it will look weird in the scene view, but from the game view, it will look correct. Let's create a script. Call it rotate z towards camera. In our script, let's create a field for our camera transform, private, because I don't want any other class to access it. Then type will be transform, because we want reference of type transform. Then we will call it camera transform. In the awake method, let's get the reference. So camera transform equals camera dot main. It will give us the reference of camera component tagged with main camera, and then we want transform, so dot transform. Perfect. In the update method, first we will find the direction from our game object to camera, and to store it, let's create a vector 3. Call it direction vector equals camera transform dot position minus our object's position, so transform dot position. So we have our direction, let's normalize it, so direction vector dot normalize. Finally, we will assign our normalized direction as the forward axis, aka z-axis, so transform dot forward equals direction vector. That's it. Save, head back into Unity, attach our script to sphere, and let's test. Let me hit the play. Let's move our sphere, and then it will going to rotate in the direction of camera, so the effect won't go off center. In the scene view, it will always going to point towards the camera, no matter from whatever angle you set it, just like that. Now a quick note, if you are on HDRP, this is the only applicable method. Next one won't work in the HDRP. Let me just remove our script. And the second method is almost exactly the same, except that we modify our shader so that instead of rotating our object, we apply our texture perpendicular to the direction vector. So if our sphere is here, we will find the direction vector from our object to the camera, then we will normalize it just like this, assume we normalized it, and then apply the texture perpendicular like this. This one is a tad bit complicated, so stay with me. Let's go in our shader graph. Let's find the direction vector just as we did in our script. So let's create a camera node. Now this node is not supported in HDRP, hence we cannot use this method in HDRP. We will take our camera's position and subtract it from our object's position. So let's create object node and feed its position into subtract. Now we have direction vector. We will normalize it. So now we have a normalized direction which points toward the camera. Assume that so that we have calculated this direction vector and normalize it. But we cannot use it alone. We also need x and y axis relative to our direction vector. So to find those two, we will take our direction vector and feed it into the cross product with our worlds up. So we will use the worlds up, and then we will be able to find the x-axis relative to our direction vector. Then we will take our newly found x and do a cross product with our z to find the y relative to our direction vector, just like these. Then we can apply our texture perpendicular to the direction vector using this x and y. In the shader graph, let me call this one z-axis. Take its output and feed it into the cross product. And the worlds up will always going to be 0, 1, 0. So we have x-axis here. Then we will take our x and feed it into another cross product, and then take our z and we have our y-axis. Now everything we are doing here, the order of operation is very important, so pay attention to that. Okay, we have all three axes, but we need a way to combine them, so we need to create a matrix. Matrices are a broad topic themselves, and this has already become a very long video. In fact, if I were to explain matrices, I need to create a separate series for that only. But just a TLDR, matrices are used to perform operations on vectors such as translation, rotation, scale, shear, etc. Now let's create a matrix construction node. So here we go. Then we will feed our x, y and z respectively. So take our x, then our y, then our z. Now we have a rotation matrix, and since we are not dealing with translation, we can take this 3 by 3 matrix and feed it into the multiply node. Once again, the order of operation is very important. Then we will use this normal vector and feed it into this multiply, and we will set the space to world. Now I know this is complicated, but what we have done here is in the multiply we have rotated our vertices of sphere in a way similar as if the local z-axis points towards the camera, and recalculated the normals based on the rotation matrix. Finally, we will feed this multiplies x and y to our UV. Now since we need x and y, we don't need a split node. It will automatically take the first two components. Then save our graph. Now in the scene view, if I zoom out, yep, if I move the camera around, yep, and if we rotate our sphere, yep, the scale, yep, and the camera node will return the viewport position in the scene view, and in the game view it will actually return the camera's position. Our shader graph will look something like this at the end, and yep, that's it for the video. If you find the video helpful, consider like, share and subscribe. If you have any questions, post them in the comments. That's it from me, and I will see you guys in the next one.